Morning, everyone. We're just going to give another minute here and then we'll get started. All right, we'll get started here. So good morning, everyone. Just really want to thank everybody for taking their time to come to our next edition of our Continuing Education Hour series. So today we have David from LG presenting for us. He's going to be covering a couple of different topics. One is an overview of VRF and technology and applications of it. And then he's also going to go over the new CSA B52 code and how it relates to VRF designs. All of our webinar series are recorded and then placed on our website after for viewing. So if you want to go back and check it out or rewatch it, they're all available on our website. And then we'll also be sending out certificates for everyone that attended today's webinar presentation as verification that you completed an hour's worth of continuing education hours. So I will pass it over to David to run the presentation.
Okay, thank you, Justin. Hello, everyone. My name is David Kim. I'm the engineering manager with the LG Electronics Canada. I thank Odell first for giving me this opportunity to speak about VRF technology and some of the cool applications with the VRF and some of the changes that are happening in the refrigerant in the coming years. We have a lot to discuss today, so I'll go ahead and then start the presentation. So first, the things that I'm going to be talking about today is basically a basic VRF overview of what the VRF is, some of the VRF benefits, and some of the VRF product range, not only focusing on the air source, but then also the water source as well, and giving some ideas about special VRF application. And then from there, I'll be moving on to discuss about the new refrigerant change that are happening based on the CACP 52 2023 edition, and also, excuse me, also the UL 60335-2-40 third and fourth edition. And I'll give you some examples of the calculation that is going to be done on the VRF side based on those two new codes. So in Canada, there is a big discussion about trying to get net zero emission by 2050. So Canada has joined over 120 countries in committing to be the net zero emission by 2050, including all other G7 nations such as United Kingdom, United States, Germany, Italy, France, and Japan. And they have released something called 2030 Emissions Reduction Plan, which is to reduce our greenhouse gas emission by 40% in comparison to 2005 emission. Okay. If I go to the next slide, it kind of gives you the idea of where we are at in comparison to 2005. In 2005, the total emission, we're sitting at 761 megatons CO2 equivalent. And right now in 2022, we were reduced down to 708. Which is a 7% decrease in comparison to 2005, which means we still have a long way to go in the overall emission reduction as well. However, if you look into the building sector, which covers around 13% of overall greenhouse gas emission, we are actually increasing in comparison to 2005. Our target given by the 2030 emission reduction plan was to reduce by 37%, which is 52.9 megatons by 2030. But we have actually increased in comparison to 2005. We're sitting at 88.8, which means we have a lot of work to do in reducing the greenhouse gas emission. And that's where the VRF comes in. The VRF, not sure if everybody knows what VRF is. Just to give you an explanation about the VRF based on the ASHRAE handbook, the VRF is a multi-split system. It is a split system air conditioner or heat pump with a single refrigerant circuit. I'm not going to read the entire phrase, but then it's a very simple heat pump system, and it does not require any gas. That's the biggest portion. If you use the VRF system, it's going to be the perfect application to meet the current electrification that is happening across the country, right? And if you look into the VRF system components, it is very simple. Many of the VRF manufacturers have their controls built into their system, and so it does not require any additional, control system in order to operate the system other than just the communication wiring between the outdoor and indoor. And so basically, if you think of it, just connecting the indoor unit to the outdoor unit with the refrigerant pipe with the communication wiring will operate the system. It's as simple as that, right? And most of the VRF systems are modular, meaning it can be added with multiple outdoor units. It doesn't have to be a single outdoor unit system, but you can have 2 outdoor units or 3 outdoor units to make up one big refrigerant system. And so the VRF is a very simple system in comparison to the other technologies out in the market. Within VRF, there's 2 different types of technology available, one called heat pump system and the other called heat recovery system. Heat pump system is basically, we call it a 2-pipe system in some of the manufacturers. Basically, it's a 2-pipe going to the indoor unit. There is no distribution box or heat recovery box in the middle, but then the downside of it is that the indoor units that is connected to an outdoor unit cannot do simultaneous cooling or heating operation. All indoor units that are connected to a single refrigerant circuit has to be in the same operation mode, either in cooling or in heating. On the other side, the heat recovery system, there's 2 different types of heat recovery out in the market right now. There's a 3-pipe system that uses the 3-pipe connection between the outdoor unit to the heat recovery unit, and also the 2-pipe system that uses a 2-pipe connection from the outdoor unit to the heat recovery unit. Depending on the manufacturer, they will have different types of the heat recovery method. But then the basic concept is the same. Simplicity-wise, the heat recovery system will allow simultaneous operation of both heating and cooling in both indoor units. So you can achieve one portion of the indoor unit operating in cooling, while the other portion of the indoor units operating in heating. Now, this is a very efficient way of operating the VRF system because basically, as the term goes, we're recovering the heat. Especially when the cooling season, rather than dumping out the heat to the outdoor, we're reusing that heat to heat the zone that requires heating. So we're recovering the heat. That is why it is called heat recovery. And depending on the situation, there's pros and cons for both 3-pipe and 2-pipe systems. So please contact your manufacturer or your distributor to see the benefit of each of the system. And just to compare the VRF, just to talk about the benefit of the VRF, one of the biggest benefit of the VRF is the size of the equipment. So the size of the condenser in comparison to the other equipment is significantly less. So for this example, I've used the 100-ton system for a comparison. The biggest single frame unit out in the market right now is 20-ton. So basically, I'm using a 5 outdoor unit, VRF outdoor units to make up for that 100-ton system. The total square feet of this 100-ton VRF comes out to around 52 square feet. And with the VRF, that's pretty much all you need on the condenser. You don't, and the condenser and the indoor units is basically all you need. On the flip side, if you want to go with the water source unit, the air-cooled chiller 100-ton unit is around 86.2 square feet. The chiller itself is already significantly larger than the total combination of the 100-ton VRF system. But then for the chillers, not only you need the chiller itself, you need the boiler, right? That adds on to additional square feet to already bigger system. If you want to go with the water cooled system, yes, the water cooled chiller may be slightly smaller than then the air-cooled chiller, but now you're going to need a cooling tower. Along with that, you're also going to need a boiler on top of it. So the overall square feet is going to be a lot significantly bigger than the VRF system. Not only that, with the water-cooled system, you're going to need a lot of valves, a lot of pumps to flow the water across the building. So there's going to be a lot of equipment and accessories that are going to be built into this building itself in comparison to the VRF system. Having more equipment in the building means that there's going to be a lot of more structural that is going to be required because of the weight of the equipment that is being installed in the building as well. So overall, with the VRF system, it's going to be at least, this is not at most, but at least 32% smaller footprint and at least 49% lighter in weight. Flexibility is another benefit of the VRF system. Is one of the benefit is that a lot of it, in comparison to the previous generation of the VRF systems, a lot of the piping limitation has been increased, and some of the manufacturers has maximized the pipe length to go up to 3280 feet, which can pretty much cover the most of the building's requirements. And also the elevation difference between the outdoor and indoor unit can be maximum of 360 feet, which means that depending on how tall your building is, you may not require any mechanical room in the middle of the building to place the outdoor units. You can place the outdoor units on the top of the roof, on the rooftop, and also on the ground level to cover the maximum height of 720 feet without having any mechanical room in the middle, right? So having said that, also the condensers can be fitted into the service elevator easily, which means you're not going to require heavy lifting cranes or even have to carry the equipment by helicopter or whatever. It's going to be very easy to transport these equipment in comparison to the other technologies out there. Having said that, the VRF serves a lot of benefits across sectors. So low initial investment because we're using a simple components and simple refrigerant piping across the building. Lower maintenance costs because basically all you have to do is just clean the heat exchangers and change the indoor unit filters for the basic maintenance. Maximize the available space by reducing the equipment size as much as possible. Lower operation costs using the high efficient inverter compressors that are available across the VRF units in the market. Total air conditioning, total solution, individual indoor cooling and heating control using the heat recovery systems. Environment friendly using the zero ODP refrigerant as R410A. I'm going to talk about the R32 refrigerant in the later slide. User convenience, individual control over the own indoor unit, not relying on the overall duct system, and reasonable payout as well. And having said that, I'm just going to go into some of the VRF products that are available in the market. Okay, most of the products that are available can be broken down into air source and water source. Air source equipment basically means that we're doing a heat exchange between air and refrigerant. Water source basically means on the outdoor unit is doing the heat exchange between the water and refrigerant. Now, most of the air source comes with three-phase units and also the single phase for the lower capacity units. Okay, most of the three-phase units out in the market are top discharge, three-phase, and it's a modular system, meaning that you can combine multiple systems to create a bigger capacity. Same thing with the water source units. They're a modular system that you can make up higher capacity combining multiple outdoor units together. But going through the air source VRF, most of the VRF out in the market right now can go down to -30 in heating operation. However, because these are air source units, there are some downside of it, and this is present for all heat pump system, which is heating capacity derating, right? As the outside air temperature decreases, the heating capacity also decreases. And a lot of the manufacturers has been trying to overcome this in a various ways. And some of the ways that we've been trying to do is one of the example is something called vapor injection. Some other manufacturer may call it differently, like flash injection, but the concept is the same. Basically, we're introducing a mid-pressure refrigerant while the compression stage to create a double compression effect. And by using this, we can basically achieve a higher pressure level while while having a less discharge refrigerant temperature. And this technology has been proven to work very efficient at the low ambient condition. So this technology has been utilized by various of manufacturers for the VRF equipment. Some other technology includes the defrost by humidity by introducing the humidity sensor on the outdoor unit to delay the defrost operation as much as possible to increase the heating operation time, such as the oil recovery by oil sensor to reduce the oil recovery operation that disrupts the heating operation again. And lastly, introducing the hot gas on the bottom coil also to prevent any issues with the frosting on the heat exchanger, any ice accumulation on the heat exchanger that could damage the outdoor unit heat exchanger. So many of the manufacturers are developing different types of technology to improve the heating performance for Canadian regions. However, and also on top of that, many of the manufacturers, they are incorporating some of the ways to add in the supplemental heat. Some of the ways could be the built-in electrical heaters on the indoor unit itself, or by providing the relay that will enable the auxiliary heater based on the manufacturer's logic. Basically, when the system realizes that due to the heating capacity D ratio, if it's not efficient or if it's not sufficient enough to maintain the heating demand on the room, it will signal to turn on the auxiliary heater. So those logics are already embedded into many of the VRF manufacturers' VRF system. However, this is a little study that I did last time that shows the number of hours that the Toronto was in during the last heating season. So many of you guys, if you're located in Toronto, you'll notice that the last winter time, it wasn't that cold. It was kind of warm winter. But based on the temperature data given by the Toronto International Airport location, the number of hours that we went down to below minus 15 was 0. Okay, last year during the last season, October 2023 until April 2024, we never went below minus 15 C at Toronto International Airport location. The reason why I'm emphasizing that minus 15 C is that the most of the VRF equipment they can provide 100% heating capacity down to minus 15 C or down to minus 12 C, which means that we can operate the VRF as a primary heating source without any auxiliary heater built into the system. So basically, without having these options to have these external heaters or the electrical heater built into the unit, we can only use the VRF as a primary heater without seeing any heating capacity ratio. Not only that, the COP at that minus 15 C, many people are like, okay, in order to provide that heating capacity, our COP is going to be significantly less. Yes, it is going to be less than the rated condition, but still it is a lot efficient. So the COP at minus 15 C is around 2.85 for the 12-ton system that I've used to make an example of. And the same system at minus 30 C, it is still showing 2.26 COP. So it is a lot efficient even at the low ambient condition. And what I've been seeing in the market on top of this is that a lot of the condos that are being built across Ontario region, the cooling demand is a lot higher than the heating demand nowadays because of the smaller rooms and a lot more heating equipments that are being built in, like refrigerators, kitchen ovens, and all that. The cooling demand is higher than the heating demand. So, if you design the system based on the cooling demand, you're already oversizing for the heating capacity. And even with the derating that you're seeing with the low ambient condition, you can satisfy 100% heating demand even with the VRF, even with the VRF, the D ratio that's happening because of the low ambient condition. So having said that, I can surely tell you that the VRF can be used to overcome the derating in Toronto, Ontario region. And now going into the water source VRF system, the water source uses the pros of both chiller and air-cooled VRF system. Some of the biggest pros of the water source VRF system is that it does not rely on the outside air temperature. So if the temperature goes below whatever minus 40 or minus 50 in an extreme winter up in the north, as long as you have a proper water supply to the water source VRF, there isn't going to be any derating happening on the heating capacity. So in comparison to the water source VRF to the air source VRF, the defrost operation on the outdoor unit is not required. The performance derating will not happen as long as you have a proper water supply. Installation location is usually the indoor for the water source VRF. And yes, you're going to need a water system, either through the geothermal or cooling tower and the boiler system. Efficiency, because there is no derating, is typically higher than the air source VRF system. And because there is no derating, you don't need the auxiliary heat. And you can do indoor heat recovery and outdoor heat recovery. And I'm going to talk about what that means in a later slide. The geothermal operation is available. And the refrigerant amount is less because the heat exchanger on the condenser of the outdoor unit is a lot smaller in comparison to the air source VRF. So with the water source on the indoor units is basically identical to the air source VRF. We have a heat pump operation and heat recovery operation. So with the heat recovery, we can basically do a simultaneous operation of cooling and heating. Excuse me. And basically, the indoor units can transfer heat and cool between themselves. When I said about the outdoor unit heat recovery, if you have multiple water source outdoor units connected to a closed loop system, if one single condenser goes into cooling while as the other units is in heating, they can do the heat transfer between themselves as well. Which means in that case, you don't have to absorb or emit heat to any of the heat source that are listed here. Right? So we have a double heat recovery system, indoor units and heat recovery between the outdoor unit, which makes it a lot more efficient compared to the air source VRF system. Okay, and this is some of the examples that some of the applications that you can utilize using the VRF. I use the air source VRF as a diagram example, but then you can utilize this based using the single phase smaller capacity VRF system and also the water source system as well. The diagram that I have shown here is the integration with a third-party AHU, right? The VRF, many of the VRF equipment are capable of communicating with a third-party AHU using something called communication kit and also the built-in EEV kit. By using these two accessories and control kits, you can control the AHU based on the return air temperature, which basically make it just like any other VRF indoor units. And also, depending on the application, you can also make it as a supplier control as well, right? So basically, if you have any example of like a makeup air unit or direct air unit, if you want to control based on the supplier temperature, we can utilize that using a VRF system. Each of the manufacturer has a different ways of communicating the third party. So if you have a project that you're working on, like to utilize the VRF, please contact the local guys, and then they will be able to supply you the right application for you. And some of the example, the top one is a return air communication method, and the bottom is a supplier. And one other application that we can utilize using this similar fashion is hot gas heat reheat. So I've been getting a lot of inquiries about using the heat recovery system to do reheat. And basically, we can use this application to do the reheat for dehumidifying during the cooling mode. So basically, the main coil will be in cooling mode, while as the reheat coil will be in heating to make up for that to achieve the required supplier temperature. Some of this application is possible using this communication kit. And some of the manufacturers also supply this hydro kits or hydro indoor units. This is basically the opposite of the water source VRF condenser. While the water source VRF condenser was the outdoor unit, was considered as the outdoor unit, these hydro kits is considered as the indoor unit. So basically what you can do is you can connect this to the air source VRF and achieve air to water heat pump system. Some of the hydro kits can have the output of 131 Fahrenheit, but some of the hydro kit that has the cascade system can produce up to 176 Fahrenheit or 80 Celsius of hot water. So utilizing these hydro kits, you can actually achieve different types of applications. I've seen an application where it uses for the domestic hot water or for in-floor heating. There's different ways of applying this HydroKits method as well. So, and again, if you have any of this application, please contact us and then we'll be able to give you more of the detailed applications to it as well. Okay, and each of the manufacturers has different types of the control method as well. These are some of the examples that can that is shown to give you an example. Some of them are dry contact controllers, meaning that we can receive the contact signal and determine the operation of the indoor units. Many of them has a central controller that monitors the entire VRF, and not only one VRF system, but then multiple VRF systems. And these guys can act as a gateway for the BMS, BACnet, Modbus networks for the total BAS connection. The remote controller is obviously different for each of the manufacturers. They have their own benefits to it and different kinds of water thermostats depending on your application. And also the power distribution indicator for billing purpose, and also the auxiliary heater relay kit, as I mentioned earlier, to connect with the auxiliary heater for supplementary heat. And the third-party DX coil controller, which I've shown you earlier for the third-party AHU communication kit. And also the contact module for the outdoor unit for Modbus connection as well, and additional contact signal connection for the outdoor units as well. Having said that, finished the VRF portion of it, and then I will be talking about the new refrigerant change and some of the changes that are happening on the VRF portion. After this, I will have if you guys have any questions, I'll have a Q&A session where you guys can ask me a question and I'll try my best to answer those questions. So as most of you guys know already, we are facing an era where we have to introduce a new refrigerant. So back in 1987 with the Montreal Protocol, we have decided to phase out the R22 refrigerant and then introduce the R410A that has a 0 ODP. But then the downside of the R410A is that it had a high GWP rating, which is 2088. This 2088, so basically the GWP means is the equivalent of the same CO2. So CO2 has this GWP rating of 1. So when many people talk about the greenhouse gas effect, they use the CO2 as an example, which traps the heat inside and then makes the earth hotter. So basically, R410A has GWP rating of 2088, which means that it is more likely to trap the heat 2088 times more effectively than the CO2, right? So having a higher GWP means that it can cause more greenhouse effect, and that is why during the Kigali Amendment, they have decided to reduce the GWP requirement down to further down than 2088. Okay, so there are two refrigerants. Oh, before that, let me talk about some of the phase out period for the R410A. So down in US, the EPA has announced earlier and given out the exact phase out schedule of each of the product category. So based on the EPA, the residential, light commercial air conditioning, and heat pump system, their GWP limit is shown as a 700, and their phase out is by 2025, January 1st. VRF is January 1st, 26. However, the ECCC in Canada have not yet released any dates for the phase out of R410A. And only recently, the HRAI has proposed some of the dates to ODS HRAR to phase out the mini splits and VRF. And those dates are January 1st, 2026 for the mini splits and January 1st, 2027 for the VRF. And note that this is only the proposal. This is not the final date, so don't be mistaken. The final date that's going to be given out by ECCC may be different than this because this is just a proposal, okay? And some of the specifications of the A2L, the two highest contending refrigerant out in the market right now is R32 and R454B. Okay, I have listed some of their characteristics in this chart, for example, in comparison to the R410A. Both R32 and R454B has the GWP lower than 700. R32 has 675 and R454B has 466. Okay, the key thing is that they're considered as A2L. Okay, A2L means it's slightly flammable. And it's not like propane or butane that can ignite easily, but R32, R44B is very slightly flammable. And let me give you an idea of how hard it is to ignite these two refrigerants. Okay. So in order to ignite the refrigerant, it has to be within the same certain concentration within the air. And if it's under the LFL, which is the lower flammability limit, or above UFL, which is upper flammability limit, it is not going to ignite. If it's under LFL, it is going to be too lean to burn. If it's above UFL, it is going to be too rich to burn. Okay. And both propane and butane being A3, they have the LFL of 2.4 and 3.0, which means the smallest concentration within the air can basically ignite these two refrigerant. Whereas the R32 and 454B, they both have much higher LFL compared to propane and butane. So it is very difficult to ignite the the A2L refrigerant. I wish I can show you that video where I saw on YouTube where they tried to ignite the R32 gas and they placed the ignite source right onto the refrigerant. I mean, you can kind of see how the gas catches on fire, but as soon as you release the ignite source, as soon as you remove the lighter, it does not ignite itself. It would be in a different scenario if you use it with a propane or butane. They would not be alive to take that video. So as this rest assured, R32 and R454B is very difficult to ignite. And out in the market, we've always been following the CACB 52 code with the R410A. But now with the A2L refrigerant, we also have to follow the the international code, which is UL 60335-2-40. And now let me give you an example of the CSA B52 code first, and then I'll talk to you about the UL. Okay, there were some of the additions that were introduced on the CSA B52 code when it was updated last year, December. And then it introduced some of the criteria and guideline on how to utilize and how to install the A2L refrigerant equipment. One example is they introduced a formula to calculate the effective dispersal volume charge. This formula can be used if there is an air circulation initiated by the refrigerant detector or continuous air circulation. So basically, if the refrigerant detector detects that there is a leak, the fan must operate to circulate the air. This is not to displace the refrigerant or ventilate the air. This is just to circulate the air within the zone. And by using that, we can basically double the RCL, the refrigerant charge limit of the refrigerant. For example, I use the R32 as an example to show the effective dispersion volume of 1,000 cubic feet. The 1,000 cubic feet, if you remember, if I go back to the previous slide, the 1,000 cubic feet RCL limit for the R32 is 4.81. For 454B is 3.06. If you compare that to the R410A, which is 26 pounds, this is significantly small, which means that you're going to need a larger volume in comparison to the R410A. Having said that, R32 having a 4.8 RCL, if I have the continuous air circulation or the air circulation initiated by the refrigerant detector, now that has been doubled to 9.55 pounds for 1,000 cubic feet. And that is why many of the VRF manufacturers will have the refrigerant detector built in and will initiate the air circulation to double the effective dispersion volume charge. Another update that kind of was interesting was the natural ventilation equation. So in previous CHCP 52 and also the ASHRAE 15, they didn't really talk about the natural ventilation. They didn't talk about the limit of the natural ventilation, the location, or the size requirement for it. Basically, you could basically have, you were able to get away with having a natural ventilation on top of the wall and then consider that as a natural ventilation. However, as you guys all know, the refrigerant is heavier than air, and then it will start to accumulate from the bottom. And having a natural ventilation up on the roof is not going to do anything. It's not going to be connecting that refrigerant that is being accumulated from the bottom to the other side of the wall. And that is why the new CSCP 52 code have this limitation that the natural ventilation has to be on a maximum height of 12 inches, 1 feet from the finished floor level. So the ventilation cannot be greater than, cannot be located higher than 12 inches from the finished floor. And also it has this formula to calculate the required area for the natural ventilation to be considered as a natural ventilation that connects with the room other side. Another thing that is introduced is a releasable refrigerant charge. So this concept is very ideal for the A2O refrigerant that has a small RCL value. So the concept is this. The concept is that when the leak, with the R410A, what happens is that if the leak happens at a certain location, the entire refrigerant within that system will have to leak. There is no way to stop the leak, entire system's refrigerant to leak from that leak source. However, the concept of this is to introduce the shut-off valve, which will initiate when the leak is detected. So when the leak is happening on the indoor unit, the shut-off valve will close itself so that only the refrigerant trapped inside this branch will leak, rather than the entire system being leaked into through this leak source. So the formula to calculate the refrigerant leak is listed in the B52 code as this. So there's 3 sections here. Basically, the number one is the refrigerant leaked while the leak is detected. Okay, and then MR2 is refrigerant leaked while the shut-off valve was closing. And the M3 is basically the refrigerant leaked after the shut-off valve has closed. So basically the liquid and gas line and the indoor unit heat exchange of volume. Combining all that, you'll be able to calculate the M releasable charge. And rather than using the entire system to calculate the refrigerant charge limit, you can use this MREL, the releasable charge, as a replacement. And this reduces the amount of refrigerant that leaks into the room significantly. And I will show you an example in a later slide. And lastly, one of the key things that I would like to mention on the B52 code is the mechanical ventilation formula. So it kind of gives you the CFM value calculation to be considered as a the valid mechanical ventilation. And now I'll talk about the UL code. Okay. Basically, the CSA B52 code talks about the volume. So it's with the R410A, it's 26 pounds per 1,000 cubic feet. But for a very over-exaggerated example, consider a room 2 feet by 2 feet, 250 feet high. That is going to be 1,000 cubic feet. Based on the releasable charge limit, we can have a 26 pounds leaked into this room. Okay. But then, as mentioned earlier, the refrigerant is heavier than air and it will start to accumulate from the bottom. The scariest part is that about the refrigerant is that it's going to displace oxygen and can cause suffocation to the human being inside that room. And that is why we have this limit. However, in comparison to this 2 feet by 2 feet, if you have a bigger square feet, the amount of refrigerant that is going to be accumulated is the same, but then the height of this accumulation is going to be different. Right. I know this is a very over-exaggerated example. I don't think there's going to be any occupied room with 2 feet by 2 feet. But that's the basic one of the reasons why the UL code regulates based on the area rather than the volume. But then the problem is that the UL 60335-2-40 has two versions that is being referred to right now, the 3rd edition and the 4th edition. Down in the US, they have something called SNAP rule that allows the R32 equipment to be installed. And the SNAP rule refers to the 3rd edition. But the only reason why they refer to the 3rd edition is because the SNAP rule was released before the 4th edition was released. And the CSA and ETA have announced that they will only allow 4th edition starting from next year. So which means that the SNAP rule will eventually have to change, or the CSA ETO will also allow 3rd edition because the SNAP rule is also allowing the 3rd edition as well. So the key difference between the 3rd and 4th is basically the formula that is being used to calculate this MREL is different. 3rd edition is a lot more stricter in calculating compared to the 4th edition. As you can see, the basic comparison to the MREL, whereas the 4th edition, there is no multiply by 1.3. The 3rd edition multiplies by additional 30% in addition to the existing comparison, existing formula that is listed out here. And the formula itself is different. The formula basically is the liquid line volume, vapor line volume, and the indoor unit coil volume. And this 0.204 is basically the refrigerant leak while it was detecting. And the refrigerant leak while it's detecting is obviously a lot significantly lower on the 4th edition compared to the 3rd edition. So there's big difference between the 3rd and 4th. But many other manufacturers are developing their system in compliance to both 3rd and 4th right now. But then, as I mentioned, the CSA and ETA will only follow the 4th edition. And this is basically the view of the VRF system with the shutoff valve. Basically, you're going to have the shutoff valve kit. This is the shutoff valve kit that I've shown here. But then another way of having a shutoff valve kit is to embed it into the HR system on the heat recovery system. Some of the manufacturers will have the heat recovery system with the built-in shutoff valve. Okay, but then this is just an example as a kit. So you're going to have a shutoff valve, indoor unit, and also each of the remotes or any additional alarm source that can act as on refrigerant leak alarm. You can basically have a dry contact to initiate the mechanical ventilation as well. But basically, this is the new layout that you can expect with the shutoff valve and with the new A2L refrigerant on the VRF system. And this is just an example that I've done using the R32 VRF system. I've used the R32 here, and I've used the LG VRF system because I have much more in-depth knowledge on this system. So just note that this example is based on the LG system. Okay. Basically, the example that I've used is a system with the R410A. So the system that you see out here is the system that designed with the R410A. However, I had an issue with the system with the existing volume charge. The total refrigerant charge here was 98 pounds, and I already had the volume, the room volume that I wanted to place this was around 3,500. And the minimum room volume with this charge, it was already like 3781 cubic feet. Therefore, what I ended up doing here was to split this system into two. However, I was like, okay, let's see how it would turn out if I use this with the R32. Obviously, because we don't have the R32 VRF yet, I have made some assumptions. Some of the assumption includes the refrigerant charge of the R32 is going to be the same as the R410A. Realistically, it's going to be slightly less, but I'm going to consider it as extreme condition. So I consider it as being the same as the 98.32. I have assumed that the line size is going to be the same as the R410A. As I mentioned earlier, in the real life case, it can be smaller than the R410A, but then as I mentioned, I wanted to consider the extreme condition. And the coil volume of the indoor unit is going to be the same as the R410A. So as per the UL 603325-2-40, third edition, this is the calculation that I have done. I'm not going to go into the detail about the calculation, but basically using this, the maximum charge that is shown turns out to be 3.43 pounds. And multiplying that by 1.3 gives me the MRO as 4.46. And I use this minimum area formula that is listed in the UL to calculate the minimum square feet that I can have using this system. And it turns out to be 64.9 square feet. Okay, so according to the third edition, the minimum area that I can have is 64.9 square feet, which is really, really small, which means it's good for us. And according to the fourth edition, same idea, same concept, use the same formula that is listed in the fourth edition. It gives me 74.7 square feet. The reason why I have a bigger value on the fourth edition is when I'm calculating the minimum area, there is a factor called H, which is the height. On the third edition, it asks for the room height, whereas the fourth edition, it asks for the indoor unit height. And because for this example, I'm using the vertical AHU sitting on the third feet stand, I had to use the 3 feet, and that resulted me having a higher area in compared to the third edition. Even with that, the minimum area of 74.7 square feet is very, very small. Now going with the CACB 52 code, there is some issue because it doesn't really talk about the ratio of the mixed volume inside the indoor unit. Because within the indoor unit, there's going to be both gas and liquid. And in the third and fourth edition of the UL, it specifically lays out the ratio between the between the liquid and the gas. And because the B52 code doesn't state that, I'm just going to use the third edition as an example because it had a higher mixed value density. Okay. And calculating on that, it gives me the total effective dispersion volume to be 3.564 pounds. And using this effective dispersion volume charge calculation, I can calculate the volume of this using this MREL, and turns out to be 373 cubic feet. Remember how I mentioned earlier that with the R410A, the limit on it was 3,700 cubic feet. And because of that reason, I had to split the system using this R32 system and utilizing the shutoff valve. I can reduce this volume by tenths. And having said that, I just want to finalize saying that a lot of people may have concerns about the VRF. You're going through the with the A2L, that because the A2L refrigerant has a smaller RCL, there's going to be a lot more restrictions on designing, a lot more limits on the design with the VRF. Going through this using this shut-off valve concept, you can actually make things a lot more easier to design, a lot more flexible to design. So please contact your local VRF manufacturers or Odell or any other distributors for detailed information on how to design the VRF using the A2L. I know that each of the manufacturers are coming up with their own design softwares to help out skipping all those formula that I've shown. I'm not expecting you guys to go through this formula every single time when you're designing the VRF system. But many of the manufacturers are designing or creating these programs to make your life easier. So I would just want to finalize saying that the VRF system is with the new A2O refrigerants, it's going to be a lot more easier to apply to your specific application. Thank you very much for listening to my presentations. If you guys have any questions, feel free to ask me, write in the chat or consult with the Odell guys. And thank you very much.
Thanks, David. Appreciate it. Yeah, like you said, if there's any questions, you could toss them in the chat now. We'll give people a couple minutes here to ask questions. And if there aren't any, then we can close it off for the day. But we'll give people a couple minutes to ask questions here if they would like.
I guess, Justin, you get an answer about the recording website portion?
So on our website, there's a section called webinars. And under the webinars section, there's a link to all of our previous recordings. And we can, what I'll do is I'll copy and paste a direct link to that part of the website here in the chat. While I'm doing that, David, if you want to get the next couple questions here.
Yep, for sure. The maintenance portion of the indoor unit heat exchanger, honestly, it really depends on the installation scene. I would suggest 4 to 6 months. But then, like, depending on where the indoor unit is installed, you might have to do the heat exchange cleaning a lot more often. And also when you're operating the indoor units. For example, I've seen a case where the indoor units were operating during the pre-construction stage, and all the dust were collected in the filter. In that case, obviously, you need to clean the filter more often. Or if you place in commercial zones where the dust is more easily be collected, yes, you got to clean it more often. But yes, 4 to 6 months is my go-to timing usually. And yes, I will share my presentation with Odell, and then I guess you guys will be uploading the same file in that webinar section as well.
Yeah, we can do that.
So does the constant ventilation like doors to each space count towards the air movement created for charge? I don't exactly know what the question means, but if I'm not mistaken, if you're using a DOAS and then if you DOAS is kind of easy to install because DOAS units are usually being supplied to multiple zones, right? And then the unit itself is either in the mechanical room that is considered as not unoccupied, or in the rooftop, which is outside. And so the zone that is being supplied to is pretty big in comparison to the ductless systems that are being installed in a smaller zone. So I'm not too sure if that answers your question, what if it added to the charge, but then it's usually not an issue with the DOAS. LG is still working on creating a latch program that is web-based. Yes, we are still working on creating a latch HVAC as a web-based. Still on the go. We're probably going to launch that along with the R32 calculation method.
Yeah, like David mentioned, if there's any other questions that come up after this, feel free to reach out to your local rep, and we can get all of your questions answered for you. But David, really appreciate your time today. It was a great presentation. Hopefully, everybody on the webinar today got a lot out of it. Once again, the presentations are recorded and placed on our website for later viewing as well. And we'll be sending out certificates for 1 hour of continuing education hours sometime in the next couple of weeks to everybody that was part of this presentation. So thank you again, everybody, for attending, and thank you again, David.
Thank you very much for having me.
Have a good day, everyone. Bye.
Bye now.